So, ladies and gentlemen, it is now my honor to introduce our keynote speaker, Mr. Mombasawala Mohmedsaeed, Chief Technology Officer, Keysight Technologies India Pvt. Limited. Is also heading the team of industry segment experts in commercial communications, network security and testing, memory and peripherals interconnects, as well as automotive and energy solutions. Mombasawala has 33 years of experience in various technology domains in the field of electronics, 5G, RF, network security, high-speed digital and optical interface technologies, automotive electronics and network operations. So let's give a warm round of applause before we head to the top.
Good afternoon. I think we already crossed over 12 p.m. So, good afternoon, everybody. My name is Mombasawala Mohmedsaeed is my name. You can call me Momba. My wife also calls me Momba. My actual name is Mohmedsaeed though. Okay. What are we going to talk about is something that you have been seeing in the since morning. This is an electric vehicle, and 4-5 important components that you see in the electric vehicles exist. EV, is it done and dusted? No, it is not. A lot of innovations are applying in EV, but I'm not going to talk about many of them. What I'm going to talk about is what do we stare at now in EV? What's next for EV? There are 3 important things that we have to note as trends in EV. One is the charging, okay? We realize that the charging anxiety in EV cannot be done with, or cannot be solved with AC charging, and we have to move towards DC charging, and that's the trend. We are looking at charging on a high power of 50 kilowatt and above. And then that's the major trend. Several standards are emerging. Another one is a plug and play charge. Okay, you don't have to do some authentication through RFID, but you actually have a preloaded script in a vehicle. It gets onto the cloud, and we will talk about SDV with cloud. It gets onto the cloud, it gets into the system, it pre-authenticates, and then it charges the EV. The third important thing that is coming up is not V1G, that is not charging the vehicle through grid, but actually using the vehicle itself as a source, okay, of power. And why are we talking about this? There are ways in which we can use vehicle as a source of power. Why are we talking about this? Because we are staring at a very precarious situation. My introduction is done, and I handle all the verticals in the company. And I realize that the biggest challenge that we have is power. Okay, because it is not just EV which are looking at power, but a lot of AI data centers and other utilities which are needing power. If I give you a figure, today we consume 3% of world electricity in data centers. By 2030, it will be 11%. Now, who is going to bring that electricity? EV also needs that much of power. I have done the calculation myself. If I replace all vehicles in Delhi, because that's where I belong, with EV, all cars, all vehicles, and if I go for fast charging at 50 kilowatt, okay, I need 7,000 megawatt of power from the grid to charge the vehicles with the currently available stations, if I want to charge them within 5 to 8 minutes. Now, where is that power? No grid has that power, right? The grids are not ready. While we talk about a lot of fancy things, the infrastructure is not coping up, and it takes huge amount of investment for that. So for that purpose, there are several mechanisms, and in paucity of time, I can't explain you. People are looking at smart ways of doing this. Now, what is it? Instead of load shedding, instead of cutting down the power, they are looking at smart ways in which we can have the deferment of charging, we can have some reduced charging, we can have some preconditions. For example, your air conditioners actually are used not at the peak time, but they cool the place, etc. These are the solutions that we are looking at. And there is a way in which we need to find the feed to the grid. You cannot keep on creating power plants because they work on fossil fuel for now. We have the nuclear technology, but it is not so advisable to have. I mean, where will we dump nuclear wastes? Okay, and the best way to go for is the grid power through DERs, distributed energy sources, but they are very few. I mean, they cannot generate the kind of power the power plant can generate. So you feed the power from multiple sources, which are the renewable energies, not the power plant, but they have to have a compliance for the grid. And that's where you need a grid compliance highlighted in yellow. So we are staring at a situation. Electrical engineers have to do a lot of work. Okay, it's not just about solving EV range anxiety problem. It is about the infrastructure now. When we transform ourselves to a EV world, we are not just needing innovations in EV now. We are needing innovations in the infrastructure if we have to transition. Imagine the whole country by 2030, you know the targets. If we transition that fast, the grid will collapse. Okay? And let's not do it so that you don't have electricity at home also, okay? The second topic that I want to discuss about is that's the real topic, and that's the software-defined vehicle. Okay, what is it and why do we want to do that? It's a big market. It currently stands at $213 billion and is expected to be around 1.2 trillion by 2030. And why is it so? Because it provides the benefit that users see as a benefit for themselves. Okay, first is the modification in car or the vehicle itself. If I use the word car, okay, believe it's a vehicle. Okay, so in any vehicle you have a lot of ECUs, and these ECUs control different actions. In software-defined vehicles, the whole architectural shift happens. Now we are copying the learnings that we had in the telecom sector here when we transform. In telecom, we realized that separating out hardware from the control, okay, is an advantageous mechanism because you can do a lot of virtualization, and we are doing exactly the same here. We have a central processing unit and then the peripherals which are around it called zonal units, and they can control or they can act as a multiple ECUs. Now the advantage is you can fast configure it. They are implemented with FPGAs. You can fast configure it, you can adapt it. Hardware can be changed the way you want because you need a lot of functionalities and the services to be added that way. That's the way we have done in a virtualized environment in telecom sector. Okay, and then you have far more software which is loaded to enable the services. So the whole protocol stack or the automotive stack is ready, and you can expand it and other things that you can do. How is it going to evolve? And this is not an imaginary thing, it's happening. By 2036, that's the target that we have for level car, we will have a completely cloudified and a softwareized version of a vehicle. Okay, but where are we right now? We are right now at SDV, which is software controlled, somewhere around level 3, level 4. The OEMs have transitioned to level 5. They have found a mechanism, or they are investigating mechanisms of further control. So if you see here, the E2E, electrical to electronics platform, is gradually moving towards more of centralized version with a lot of compute power, peripherals and memory around, and then a lot of models that you will have to impose on them so that it becomes a true software-defined vehicles. You can do a lot of things. Software-defined, one of the features of the software-defined vehicles is then autonomy. Okay, that means complete driverless control in the vehicle, and that also needs a lot of arrangement, but we are transitioning towards that, and this is a phenomena. It's a very complex environment that we are getting into. I have gathered a lot of knowledge of, about semiconductors, being in this company, about telecom networks, but I see the KPIs, the kind of speed, the kind of reliability that we need in automotive control is far bigger and far robust than what we need in other applications. There is nothing called a reset button that you have in a vehicle wherein you stop and things become all right again. Okay, it has to work on the fly. It has to be that reliable. It has to be much more reliable than what we have witnessed. It's like, we are making a small plane. The reliability of what we have on the planes is something that we would want to replicate over here. So this is how it looks like. Instead of hundreds of ECUs, okay, this is a timer for me, right? Okay, there are hundreds of ECUs, and then the protocols between ECU and the sensors and the actuators, etc. Okay, there are all discrete protocols. We want to have a good standardization. We want to have an Ethernet based. Okay, while we have ECUs and other stuff, we have a lot of wiring. If I give you an example, if you have 100 ECU and you want to interconnect one with all, How many connections are needed? 100 into 100 minus 1 by 2, if you remember that mathematics. You don't need that many connections, but if you really do that, imagine the amount of copper that you have. 50 kilogram of copper still exists with ECUs. You want to bring it down so that the vehicle become lighter and then make it more virtualized. This is what you're looking at, okay? I don't think we will stay at copper. We'll move to fiber because semiconductor evolution also is like that. We are packaging the optics and the semiconductor together in one die. And there is a phenomena called chiplets which is emerging instead of just chips. I don't know, and automotive industry will not absolve from that. They will consume those infrastructure things as well. Okay, so what from our company Keysight point of view we look at in the automotive sector in SDV? These are the areas. Electrification, don't think about it, but the prime areas that engineers have to work for next 5 to 10 years. Okay, are communications. We have to perfect it. Okay. We have not perfected it. 5G have not perfected the communication the way we envisioned earlier. Okay, we are not meeting the targets of URLLC. We are not meeting the target of MMTC, that is massive IoTs. Okay, we need to have a robust security mechanisms. Okay, the current practices are we have the federation and then we have the common vulnerability exposures known through federation and we fix it, right? The hackers and the rogue actors will be smart enough to intrude into vehicle and it can be life-threatening. So how are we going to solve it? We don't have a red reset button, remember. Okay, the cloud backend, because the services have to be ported on the cloud. There is no alternative. Otherwise, we'll not be able to upgrade so many vehicles if you don't have a cloud-based services. You can't be upgrading, you can't be enabling features into the into the vehicles, which are so many, if they are not cloud. And then the computing. This is a big subject. I don't know how the mystery will be solved. This is a conundrum nobody will be able to solve so easily. How much of computing in the vehicle and how much of computing in the car? What models to run where and how this split computing is harmonized is an example that we will have to worry about. And then the perception of the car. These are the areas we are working on. Okay, I don't want you to worry about all these areas. Okay, fall back on us if you have these requirements. But let me get into one important part. One of the ingredients that we'll need in SDV is AI. Okay, we will need the models which are completely trained and have enough of use cases or even enough of practices that actually is able to emulate its operation. For example, braking, acceleration, comfort, lot of things. And these models are very different. And where do you execute these models? Where do you train these models? Can you train a model in a car? Absolutely no. You need a huge infrastructure, and that is this data center. Okay, so how is the data center built? And these data centers are energy guzzlers, and we have spoken about the energy. Now see what we have to solve. Lot of problems to solve. We have the data center wherein you have the primary component called computing power. That is a GPU. We'll talk about that. Okay, and then it is surrounded by memory. And then the peripherals, and you have the card ready. Several of these cards are added into card cage. You build a rack. Several of these racks are ready, and you connect it with the network. Actually, you need to connect all processors with all other processors. And I use the same equation. You need millions of connections, and that's why we use a switch fabric that you see as a top of rack. So if you go to a data center, you see a lot of racks and then a lot of cablings. Okay, and a lot of pictures are also seen in the things. But actual things are far more complicated because this becomes a fundamental to the data center, GPU. Why do you need that? Because it allows you vectorized operation, parallel processing, and it allows you to have the platform like NVIDIA's CUDA platform or AMD's, platform, etc., are allowing you to have the coding. So this becomes a fundamental block for you. And the data center AI data center is not a normal data center. In addition to the front end that you have in the data center, there are huge storage clusters And you also have a huge back-end network wherein you have extra amount of computing power. And the computing power is organized in such a manner that you have the memory access, which is available from one processor to the other processor, to the other location, attached to the other processor, even if they are at the remote site. Now that makes things far more complicated, okay? And this is a phenomena which is currently happening as we speak. Data centers are scaling. Do you have any idea about the kind of GPUs or the number of GPUs that companies like Meta use? 600,000 GPUs, that forms one data center. What Grok use, Elon Musk Grok, around 800,000 GPUs. Imagine the scale that we have used in the data center, and still they take several weeks to train the algorithm or train a model. Now, if you have a model to train the braking system of a vehicle, it would take probably 6 to 8 weeks to train. And what if you have more data coming in and you have to train again and again? Imagine how are you going to do that? And you have to load this into the vehicle. How much are you going to wait? You are not going to endlessly wait for all models to be perfected and load it onto the vehicle to roll it out into the market. Imagine that. And this is what is the performance measure of a data center. They are measured only in two major parameters: flops, floating point operations, and you will hear in most of the speeches tokens. And tokens are an extremely necessary part of training. We'll see in the next slide. The number of tokens that are serviced per watt per dollar decides the performance of the data center. And what are tokens? They are incremental elements that are needed to train the model. Now, I am taking an example where I want to train the model of braking of a vehicle. And this model is the very simplest of all I can draw on the screen. It has several variables, very few variables, but millions of tokens to be injected, and each of them have the weighted factor. These weighted factor would give you the output, and the output has to feed back to the system for convergence. All of you are engineers, I believe, and you know the control system stabilizes only when you have a negative feedback system. If I want to converge, I need to have the difference between the actual driving conditions versus the output that an AI model gives me, and then feed it back to retrain again and again and do that. What about the data? Where is this data coming from? Without a correct data, training is not complete. Now imagine a model being trained on the conditions in a developed country and implemented in India. Will the vehicle operate properly? Right. It won't. Who is going to federate the whole data and then compile it and put it for training? It's not so easy. So while stories are written about SDV, complexities are far more than what we are actually writing as stories, okay? And then I want to skip this slide. I want to go to this. By now we are convinced that this SDV is not about the NEM's play or the car makers play or the vehicle makers play. So the OEM that you see here are no longer in the capacity where they can make the vehicle which are SDV, the way they have been making the ICE vehicles in the past, okay? There are a lot of companies which are required. For example, for AI modeling, model training, you need the hyperscalers. So you see the hyperscalers there. For the semiconductor, you need a lot of semiconductor companies. You see the semiconductor layer there. For services to be enabled, you see a lot of companies on the top, like Lyft, Uber, Alphabet, Google, etc. The ecosystem is getting increasingly intertwined. And it is not one company that exists by itself. And imagine the amount of coordination that we need from companies which make chips like NXP and Infineon, etc. And then the tier 1 system manufacturer like Bosch and Conti and a lot of other companies. Now it is far more than what we envisioned in the past. SDV is not about sitting and have a luxury of a vehicle being driven. That is a user's call. That is not an engineer's call. As an engineer, we have to do a far better work in fixing all of this. And now you can appreciate the timelines of full SDV to be 2036. I am still skeptical. Will it be achieved by them? I am not sure. The way we are moving on 5G and 6G technologies, I doubt. We will not be able to do, we will be able to do a lot of things in vehicle. We probably will do a lot of things in training and modeling, but we will not be able to achieve good connectivity the way we have failed the world with 5G, okay? Pardon me for that if you get sensitive, okay? But this is a reality. And that's it. Finally, one last slide that I want to show about Keysight. I still have 26 seconds. So these are the areas that we are working on. Take a picture of this slide, fall back on us, and then these are the books that I suggest you to read. I read all three. They are on AI. Start with Age of AI, very well written about the basics of AI. Transition to the Coming Wave by Mustafa Suleiman. It talks about a lot of containment, and then Nexus, which talks about a totalitarian rule that we will be getting into with the AI age, okay? And then I never do complete my presentation without quotes. This is a very apt quote I discovered for automotive, okay? Automotive is one area, SDV is one area where we cannot afford to fail. It can be life-threatening. And this is what applies to engineers like us. To err is human, to persist in error is diabolical. We can probably make one mistake, but not the second mistake. You will not be pardoned. You will be taking somebody's life, okay? And lastly, it always seems impossible until it is done. Okay, it looks complex right now, but it will be done. Ladies and gentlemen, thank you for your time. Yeah.
Ganesh Rao from Silicon Auto. My question is on that automotive architecture that you showed, that zone architecture and all that. How much of that is driven by engineering requirement versus the business models of software subscription and upgrades?
Okay, that's a good question. So one thing which is there is, these SDVs will be more of software subscription-based features. Okay, it's not driven by the model. That model already exists. Okay, we are practicing that model in other enterprise and other stuff also. So it's not about that. It's also driven by the engineering. Okay, as we want to take away a lot of these humdrum jobs out of this automotive industry and move up the value chain. That's what we are trying to do. So it is a mix of both, but largely driven by engineering. And executing those engineering details into the acceptable market would require those business models. Thank you.
Insightful, engaging session. Your expertise has provided us with much to think about. Now I would like to invite Mr. Shailesh Shukla to the stage to present a token of appreciation to Mr. Mombasawala.